Hello and welcome you all to AN Automation. Today we'll discuss about the topic of basics of electrical drives. Uh, Firstly, we will thankful to Sir Nikola Tesla who invented the three-phase AC, alternating current. And today we'll discuss about the history behind the drive technology, why we are using electrical drive, advantages of use electric drives, and the functions of electrical drives. Okay. There are many drives we have shown here. Nowadays, generally ABB and Siemens is the main market player in electrical drives, AC drives or DC drives. There are two renowned brand is there. One is Siemens and another is ABB. So at the first, we'll thankful to Sir Nikola Tesla who have invented the AC power in 1880, and the Tesla three-phase AC motor ran on three-phase power and is one of the greatest labor saving device of the all time. It's completely changed our lives. It had our significant drawbacks. However, it could run only one speed. So many devices were invented to compensate these things, such as belts, pulleys, sieves, dampers, inlet guide vanes, eddy current couplings, fluid couplings, and so on. So it took about 100 years to develop a device that could run the motor at different speed reliably and cost effectively. In 1980, the variable frequency drives or variable speed drives were introduced. The origin of 1980 variable frequency drives offered a lot of spare space, so we are not in the small package we see now. However, the basic topology of a VFD has not changed since 1980. Over the last 30 years, nowadays, the modern drives will have the same components but will be contained in a smaller enclosure with less space packed together and often in multiples. Since their invention, VSDs have now saved billions of pounds in running cost and reduce energy waste greatly. So, electric drives were first designed in Russia in the year of 1838 by B.S. Lakovi when he tested a DC electric motor supplied from a storage battery and propelled a boat. But industrial adaptation occurred after many years, as around 1870. Today, almost everywhere, the applications of the electric drive seen. Okay, a typical drive system is assembled with an electric motor and a sophisticated control system that controls the rotation of the motor shaft. At first, the control system gives the command to the drive to control the electric motor. Then the electric drive will check there have a suitable AC supply is available for powering up its power unit. Then it will generate a square wave PWM signal, a PWM three-phase line in square wave format to run the electric motor. So let's have a brief look on that. So there have an induction motor there, and we are using a PLC controller to communicate with the motor. How it will happen? It send the controlling data via Profinet, Profibus, RS485, RS232, Modbus, Profinet, etc. to the control unit of the drive, and then the control unit will perfectly fit onto the power unit of the drive. This is the power unit and this is the control unit. Okay, so control unit is directly mounted upon the power unit, and then the power unit check rather than the three-phase input supply is proper or not. Then it will generate the three-phase output for the induction motor. We can for communication purpose or programming purpose we use a CMET PG or a laptop and use some softwares like TI portal and starter or Simoson scout to control or make a logic or parameterize the control unit or the PLC controller. Okay, rather we will if we can directly communicate with the PLC controller and control the full system via the PLC, or we can directly directly parameterize the CU to monitor and control the induction motor. Three main reasons to use electrical drive, okay, rather than the conventional system. And the first system was in the energy swing, okay. In many drives application involving constant speed operation of induction motor operates under no load condition or light load for prolonged period, such as in pressing machine, conveyors, rock crushers, centrifugal pumps, drill press, wood saw, etc., and some machine tools. In such applications, saving energy can be achieved by operating the motors at low voltage while running at no load and light loads. When a motor operates at full voltage at no load, core loss has a large value. Reduction in the voltage increases the copper loss but reduces the core loss by a larger amount. Okay, this will impact in the energy saving, and then we can control the motor in an intelligent manner by using the VFD. We can easily control the motor as per desired speed or torque. By using the modern technology like VLSI, we can control the motor in an intelligent manner. Nowadays we can control the motor monitor, we can monitor control, okay, nowadays we can control the motor and monitor the motor parameters from a remote PLC controller like SCADA screen, HMI devices, mobile or wireless controllers from a control room or home. Rather, we go to the site and checking motor parameters and control the motor from field. So this facility will always give a intelligent solution for the motor control. Okay, and the third one will be the reduction of the peak current drawn. In starting and braking time, an induction motor draw enormous current to break the pull-out torque. In modern VFD, the current supply gradually increases and decreases in the time of starting or stopping. Okay, so there have no risk of peak current drawn by the motor. This feature help to give a longer lifetime for the mechanical system. Now the advantages for using electrical VFD. The advantage of the using electrical VFD is saving the energy and improve the system efficiency. Convert the power in hybridization of application. This hybridization means actually we can use the power by let's have a look on the application of winding and rewinding. Okay, in the winding and rewinding we can see the rewinding device or drive can regenerate the power, okay, through the regenerative system, regenerative motor control unit, a motor regenerative power unit system. Okay, so we can convert the power hybridizedly, match the speed of the drive to process requirement. Okay, we can match the speed as per our requirement. We suppose we need 14,000 or 1400, sorry, 14,000 is more, 1400 rpm, we can get 1400. Other we can we from some calculated operations like winder control or diameter control method, we will have to limit the speed or change the speed as such a fraction of manner. Suppose we need a unconventional rpm, okay, let's suppose we take 1335, so we can get the 35 and 35 desired output speed by the VFD, but which we can't get from the doll starter or any other starters. Okay, so the matching the speed of the drive the process requirement is very easy in the modern VFD system. Match the torque or power of a drive to the process requirement. Okay, now the torque equation I will discuss in this video in the next slide. Okay, so this point is so important for processing the electrical drive. Okay, improve the working environment because it always improve the working environment, because there have no need of oiling or some material which can dart use create dirt in the environment or in the control room. So it's environment friendly, and also the um, clean, also helpful for keep the working place clean. Lower noise levels, for example fans and pumps. Before using the VFD, we use the normal fans and pumps to start and stop with the contactor logic or contactor, electrical contactor. Those contactors, in some cases the fans are very high rating, like ID fans, FD fans. So these types of fans needs high rating contactor also. So this high rating contactor can produce very much having noise, and very much amount of noise from its starting and stopping. Okay, and the and the cost of the contactor is more higher than the conventional VFD. Okay, reduce mechanical stress on the machine to extend their lifetime. Here, mechanical stress is a huge chapter. Okay, in that, in electrically, we can understand that if on the starting time in a doll starter or any other starter, the induction motor takes a enormous torque. Okay, enormous current to pull out the starting torque. Okay, so in that case, when it takes enormous torque, enormous current, and the current is directly proportional with the torque. So that if the torque level is more high in the such a manner for in instantaneous time, or for a small time, then the machine or machine shaft will directly damage from that, because it's take a enormous stress at a certain time of period. So it will damage the mechanical system by its mechanical stress. In the mechanical stress function, we can add the one thing. If you search in Google, you can definitely get that. In mechanical stress, there are a large amount of backlash compensation. Backlash amount is very useful for traversing or some other operations. You can get it from Google. So save the peak consumption to avoid the peak demand prices and reduce the motor size required. Okay. So before we start the drive, actual what is the drive is actually work graphically, we will have to look around the some formulas of the induction motor. We can get the from our previous sessions that sleep is, what is the sleep? Sleep is the ns minus n divided by ns, where ns is the synchronous speed and n is the shaft or mechanical speed. Okay, and we know from our college standards or before that ns is equals to 120 f by p, where f is mean frequency and p is the number of poles. Okay, so if we increase from this from the equation, we can get if we increase the pole numbers, the speed will gradually decrease, and if we lower the pole pair number or pole number, then the speed will increase. Okay, so from that equation we will definitely get that there have a change, there have one constant value, what is 120, and one is the uh, variable value. We can vary the value of f, and we can change the value of f in running condition, not in the designing perspective. Okay, but p, the pole pair, which is a designing concept, constant. Okay, so we can't change the p in the running condition because it's totally about the design level thing. So we'll have to only change the frequency, but there are a problem with the changing in frequency. What is the problem? problem is the phi is proportional. Look in the next slide. Okay, so phi is directly proportional to the v in, or price inversely proportional to the frequency. Okay, if you directly change the phi, the frequency, the phi value will definitely change. So in that manner we will have to take the phi constant. Another we formula or equivalent circuit we can get that. In the equivalent circuit, first we will notice that the R1 and X1 is the starter resistance and the leakage reactance, and R2 and X2 are the rotor resistance and the standstill leakage reactance per phase respectively. So from that equation we can get EB. If we applied a voltage in the stator part, that is V1, we will get EV. EV, what is EV? EV is the back EMF. Okay, back EMF. What is back EMF? Don't go on that definition. We are focusing on that equation to understand the drive. Okay, so we can get the equation in the same pattern. If the EV is proportional to the 4.44 multiplication of F, phi, and Z, where F is frequency and phi is the flux, and Z is the number of turns per pole. Okay, we can easily write down here the V is proportional to 4.44 F, phi, and Z. After neglecting the constant, designing the parameter, we can get the variables for change. Okay, now the 4.44 is the constant. We'll make it out. The phi and f are the variable or changeable value in the running condition, because Z cannot be changed in the running condition. Z is the term we use in the design perspective. So we can get, we after neglecting the Z and 4.44, we can get the V in is proportional to the F and phi, which can rotate the motor. But there have that means phi is equals to V by F, and this V by F, for this equation we will get the VFD for V by F control method. Now what is V by F control method and why we'll use the V by F control method? So now phi is directly proportional to the voltage and indirectly proportional to the frequency. As per the last equation, we can get the NS is equals to 120 F by P. So we can easily get, if we change the frequency, we can change the speed of the induction motor. But if we change the frequency for lowering or uppering the induction motor speed, the torque will change, because torque is proportional to phi into I. So if we change the phi f, if we increase the increase the frequency, then the flux will go down. So we can't get a defined torque here. So what we will have to do, we'll also have to change the V. So it will help us to keep the ratio of the phi is same. Suppose we will use to change, suppose let's think about that a motor gives 1440 rpm in the rpm of in the frequency range of 50 hertz in a voltage range of 400. Okay, so now if we change the f, that means 25 to get the half, like 700 rpm. But when we get a 700 rpm, the torque is also changed, because the torque is gradually decrease, because the ratio is low. Okay, then but we need a same torque. Okay, in same torque but variable, which can vary in variable speed. So if we run the motor at 30 rpm, it will give that 100% torque. If we run the motor in full rpm like 1400, then it will give a same torque. So what we will have to do, we will have to keep the ratio same, that the value of the phi will have to the same. So we'll have to change the f and and also the V. If we change the F25, then we'll have to also change the V in 200 to get a proper phi ratio, that is flux ratio. In that way we can control the torque also. We can control the speed without varying the torque. Okay, this is the equivalent circuit of induction motor. So we can see in a modern conventional drive, we can get the, we can see in the image, in a modern conventional drive we will get the following part in the system. The first one is rectifier, second one is filter, and the third one is the inverter or converter. So we will supply a three-phase input in the rectifier section. Okay, in a six wave in a three-phase bridge rectifier, we can see the diodes which will rectify the three-phase input supply. When the three-phase input supply is rectified, it's occurred a pulsating occur it rectify the DC in a pulsating manner, and the pulsating DC is filtered in the filter circuit. In the filter circuit there are capacitors and inductors, and filter circuits are defined. Filter circuit is used for filtering the pulsating DC in a DC output nearly about the straight line. Why we are saying that the DC is nearly about the straight line? Because it the DC will get in a straight line form its contents of various ripple factors. What is ripple factor, I will explain next. After the getting the ripple or linear DC, we will convert the the convert or invert the DC in three phase AC output, which is a variable frequency variable voltage output supply, which we will use to supply to the motor. This three phase supply is directly connected to the motor to controlling the frequency and the speed of the motor, and we are controlling this via the control unit, which will mounted or rather separately mounted and connected via the drive click or ethernet or any other system or any other topology with the power unit. Okay, so we'll see. At first we give the three phase sinusoidal waveform three phase supply, which is a sinusoidal three phase waveform. We will directly inject in the rectifier section, and rectifier section will rectify the DC in a controlled manner. This is the controlling of the rectifier, where you can control the rectifier. We use half control, full control, or any other angle related control we can control with the control rectifier, and then we'll get the pulsating DC. Now the pulsating DC is the black line. Okay, this AC is directly getting out from the rectifier section. After filtering the DC, we'll get the red line, which is nearly about what we say before. We will get a nearly about linear DC output. Okay, this phenomenon is called the ripple, and it have a factor, that's why it is called as ripple factor. Okay, so after we getting the rippled output of DC, we inject it to our inverter section. We'll eject it to, and inject the inverter section. In the inverter section we will get the PWM output, where the PWM output is nearly tends to the three phase supply. Okay, but it's have a manner of square wave. In that case, with the red line, which is denotes the here this is the red line is denote it's imaginary. Okay, the actual supply is that square wave format. Actual supply will get like that square wave format. format. Okay, we'll discuss about in the next slide. Okay, how the square wave format is essential for the motor, or how we can use this PWM output signal to control or to operate the three-phase induction motor. So this is the basics GIF to understand the how we can use the three-phase supply in the rectifier section, how we can get the field, what we will say, this is the pulsating DC. How can we get the a pulsating DC from the rectifier section, and then we filter to nearly about linear DC supply. Then this linear DC supply, after filtering the linear DC supply, we directly inject to the switching device or switching unit, which is IGBT unit, and we will get the PWM or RMS AC supply to control the motor. Okay, so after getting the PWM or square wave format AC, we can see the how can we control the pulsating. Okay, here in this graph you can easily say this the lines of square wave. This square wave means how much time, okay, how much time the IGBT is on to control the outgoing uh, supply to the motor. Okay, the time or the bandwidth is small, that means open the motor, open the IGBT for small time. Okay, when it's open the IGBT for a small time, then the IGBT put a low voltage or lower voltage, and in the higher matlab, in the higher section or the in the high square wave, high sinusoidal, when the voltage in sinusoidal level high, then we will have to put the IGBT on for more longer time. That's why the pulsating square wave is more open than the this one. So after switching on the IGBT in this pattern, we can get the proper sinusoidal wave as the input supply, as like three-phase input supply. We can use this square wave to pulse the to get to do the pulse in the switching on and switching off time of the IGBT to control the voltage of the output level. But we'll have to consider one thing, that the if the input or output voltage is controlled is in this manner, like this square wave, the output current is quite rippled like that. Okay, this is the output current which is rippled. So we will have to use separate drive duty selections induction motor for drive purpose. Okay, there have many company who will manufacture these types of drives which is separately designed for drive duty purpose, and if it is not a drive duty purpose, then the motor can be burned or damaged by this cost. Okay, so this is this the square wave, this is the square wave. How we can control the IGBT by the square wave? We can use GTO, which can turn off, turn on in a separate time with the reference of the square wave we will generate from the our frequency. And we will have to understand this is the voltage level we can control with the pulsating or square wave format, square wave format wave. Okay, but how we will change the frequency will change upon the set point, which set point will give it scale the frequency value to this value, and it generate that frequency, and the voltage level is controlled by this. Okay, so this is the major components we are used in modern electrical drives, that is IGBT, IGCT, GTO, diodes. GTO is most commonly used in modern technological modern technologies for making electric drives. This is the basic symbol of thyristor bridge. Okay, basically normal thyristor is not placed in the drive uh, drive. They use like that. Okay, like that thyristor bridge to control the input or rectifier unit. And these types of GTO or IGBT is used in the inverter or converter section to control the output or inverter section, or generating the output voltage in a square wave manner to control the VFD output. In this, by these components we basically used in modern VFD system to control the VFDs. So at last but not the least, that system which controls the motion of the electric machines are known as electric drives. Okay, thank you everyone. This is the end of the session, and we will update you with you the more update about the electrical drives or electrical automation related videos. So stay connected with us by subscribing our channel. Your subscribe is motivating us to make new videos and make new idea for learn and stay sharing. So stay safe, stay happy, and connect with us with subscribing and pressing the bell icons. Thank you. If you like the video, you can like in the like button, and if you have any queries or any other related topics and any other queries, you can directly comment in below section. So thank you everyone. Have a great day. Goodbye.